tutorial on Laplace transformation. First of all, we try to understand what is basically the need of transformation tool. Basically, it's a component of mathematical transformation and being incorporated in the course of the signals and system. This core signal and system is highly crucial if we are talking about the various type of competitive examination in the core engineering. Here in this tutorial, we are trying to understand what is basically the necessity of the transformation tools, specifically the Laplace transform, and what are their aspects and attributes. So let's start with the basic definition and basic correlation of this transformation tool. First of all, the first most important thing which is to be understood is what is the requirement of the transformation tool. Generally, we have basically two types of domain analysis. One is the time domain analysis and second is the frequency domain analysis. So while we are moving on with the signal in the time domain analysis, it is always tough to analyze and find out the basic detail at the very instant of time of that particular signal with respect to time. So to provide different kind of a calculation and create an ease, one should go for the transformation. So transformation from time domain to frequency domain easily converts the signal into the mathematical less complexity and easiness. So here number of the numerous tools are there in which the Fourier transforms are the most common, and here we are looking for the Laplace transformation. So first of all, it is important where we can apply this Laplace transformation. So all kind of a continuous time, linear time invariant signals, we can easily apply this Laplace transformation. So complex Fourier transform is also called a bilateral Laplace transformation. This is used to solve a different equation. Consider an LTI system excited by the complex exponential signal to the form xt. And this xt can be represented into the simplest form, which is the g e raised to the power st, where s is any complex number and that is a correlation of definitely combination of the sigma plus j omega. This sigma and j omega can be represented into real and imaginary form. The response of any LTI system can be obtained with the convolution of the input as well as the system response. Suppose that we have an input response xt and the system is to be represented by ht. The response of the system can be taken as the xt convolved with the ht. This convolution can be taken into the equation from integral minus infinity to plus infinity as h tau g e s t minus tau d tau. So convolving a particular signal with respect to the input signals and responses that we have already talked about in the previous lectures. So here one can easily get an output. This output can be represented as yt equals to g e raised to the power st hs, and this hs is being called as basically the S domain analysis, and this S domain analysis is the Laplace transform of the system response hs. So by getting this value hs, one can easily find out the response of a system in the frequency domain. So what we are doing, simply we have a system and the system has certain sort of the input xt and the system is finally a yt. So what we are trying to do, we are converting this signal xt into the frequency domain as xs, trying to convert this ht into the frequency domain as hs, and again the response which is coming because of the convolution of these two will be ys. So this is basically the relationship. Let's we have a relationship between the Laplace and the Fourier transform. The Laplace and the Fourier transform has a relationship as xt equals to xs can be represented as minus infinity to plus infinity xt e raised to the power minus st dt. This is the basic equation. This is the very basic equation of the calculation of the Laplace transformation. Any signal can be represented into the xs form with the help of minus infinity to plus infinity xt e raised to the power minus st dt. As we know, this s is generally a representation of the real as well as the complex value of sigma plus j omega. By substituting the sigma plus j omega, the expression will come up like the minus infinity to plus infinity xt e raised to the power minus sigma plus j omega t dt. Again, solving this, one will be able to get the xs equals to Fourier transform of t xt e raised to the power minus sigma t as an equation number 2. This xs is represented as a signal xs equals to x omega and for s equals to j omega. Similarly, one can have the inverse Laplace transform with the help of these equations. The inverse Laplace transform can be represented as xt equals to 1 upon 2 pi minus infinity to plus infinity x sigma plus j omega e raised to the power sigma plus j omega t d omega. That means this can be represented as xs and this can be represented as st. So by putting this value as xs and e raised to the power st d omega, one can easily get the value again as an xt. So finally this can be denoted with the help of the equation number 4, xt equals to 1 upon 2 pi j minus infinity to plus infinity xs e raised to the power st ts. So this equation number 4 represents basically the inverse Laplace transformation. So from the equation number 1 we could be able to get the basic original formula of the Laplace transformation, and from the equation number 4 one can easily get the inverse Laplace transformation. It means any transformation coming from time domain to frequency domain and back to frequency domain to time domain can be get with the help of this equation number 1 and equation number 4. Similarly, let's moving on. Some initial value and the final values theorems are there that represents where it converges. This value basically tells us that putting the value as x0 will tells us where the initial boundaries comes up. So if xt is first derivative in the Laplace transformable, then the initial value of xt is given by x0 plus, it means just being initiate, and limit s tends to infinity as xs. This tells us from where the region of convergence. It means if suppose we are trying to find out the frequency domain analysis, so from which point it is being started, that can be get with the help of x0 plus. This 0 plus tells us this is the very initial value from which this Laplace transformation has been initiated. And similarly, looking for the end value where this finally converges at the end can be get with the help of x infinity. So the relationship gives us limit s tends to infinity as xs, s tends to infinity. So by this one can easily get the initial and the final values theorem. Similarly, if suppose we are looking the more things, so we should go for the region of convergence of Laplace transformation. What exactly it means? Suppose we are looking and trying to convert this time domain signal into the frequency domain signal, so there should be some requirement where this conversion has to be defined. It may have a certain sort of boundaries. These boundaries are basically represented as region of convergence. This region of convergence comes up with the relationship between the properties of the Laplace transformation. Suppose that we have a xj omega plane, and in this xj omega plane, this is the s plane which represents as the real axis as the sigma and imaginary axis as the j omega. So the point where it lies on a s plane will gives us the relaxed value where it is stable. So if xt is absolutely integral and it is of finite duration, then ROC is an entire s plane. So we have some certain sort of rules and equations. These rules and equations help us that this xt signal is absolutely integral, completely integral, and it's finite duration and definitely having sort of the finite limits, then the ROC is entire s plane. If xt is a right-sided sequence, that is real s is less than sigma naught 0, so this real x is greater than value of sigma naught. Real values are greater than sigma naught, the real values, then it is on the right side. And similarly, looking for the third one, left side sequences can be get with the help of real of s is less than sigma naught. So if xt is two-sided, in that combination ROC can be explained by the making use of example given below. Let's take one example. Suppose that we have any signal xt, and this signal has a value e raised to power minus at ut, where ut is the unit step function defined from 0 to infinity. And try to find out the Laplace transformation. The Laplace transformation of the xt will be given as 1 upon s plus a. Under this condition, if we are trying to find out the real value is greater than minus a, ROC is definitely very greater than of minus a. So in a s plane at the value of the minus a, this region of convergence will give the area where this frequency domain analysis will conserve and resolves. Let's take another example in which we have basically Laplace transformation ROC xt for e raised to power at u minus t. This time the ut unit step function is defined from t0 to minus infinity. Under this condition, if we are looking to find out the value of 1 upon value of xt signal in the terms of the Laplace transform, so this will be equal to 1 upon s minus a. And here this s minus a will be converse if this real values of s remains less than a. So this region of convergence is less than A in the plane. So the shaded area in this figure, represents the region of convergence. So with the help of this kind of a equation and a calculation, one can easily find out if particular signal is there and this particular signal is being converted into frequency domain. So where this exists actually, where it is defined actually. So this is the requirement of the region of convergence. Let's see. In the third example, if suppose we are combining both the signal e raised to power minus at ut plus e raised to power at u minus t. So let's see, the ut is defined from 0 to infinity and u minus t is defined from 0 to minus of infinity. So the whole area from minus infinity to the plus infinity covers up here. And looking to find out the region of convergence, so again we'll go for the Laplace transformation, and this Laplace transformation gives us 1 upon s plus a plus 1 upon s minus a as a combined value. For 1 upon s plus a, it should be greater than minus a, and for 1 upon s minus a, it should be less than a. Under these conditions, if we are trying to find out the region of convergence lies between minus a to plus a. So here this complete signal defines between minus a to plus a on the real axis. So this S-plane analysis gives us if suppose someone is looking from time domain to frequency domain analysis, so from where and in which particular section it is being defined. So number of things are here. So let's we discuss later on. I hope so in this lecture you would be able to understand what is basically Laplace transformation and what is basically region of convergence. In conclusion point, let me clear it again. Laplace transformation are basically the tools which are used to convert time domain analysis into the frequency domain analysis. A requirement of time domain analysis into the frequency domain analysis is to analyze and to realize the signal in the frequency domain for expectation of different type of calculations. So the first of all easiest method is here. If we are converting it from time domain to frequency domain for a continuous time signal, so Laplace transform is the best tool. So Laplace transformation, if we are looking for, we have to find out where this Laplace transform converts. Sometime it might be possible that the conversion limit will not be existing within the time interval of the given function. So under those conditions, it will violate the rule. So if suppose someone is looking to find out this Laplace transformation from time domain to frequency domain and looking back to inverse Laplace transformation, the region of convergence has to be taken care. The simplest method is to find out the region of convergence. Try to find out the values of the Laplace transformation as we got previously here. And under these values, try to find out where this S converts. S, here in this case, S will be defined if it is having the value of greater than of minus a. And this S minus will be defined by having the value of less than a. Under this situation, try to find out the values of the real of S, create a certain band, cut certain limit. Over that particular limit, this frequency domain analysis will be converged. This lecture is basically intended to give the technical details of the Laplace transformation and the region of convergence. In the next lecture, we will try to find out the more values and how this Laplace transformation can be taken up. And what are the different Laplace transformation to the different kind of a signal. What are the basically rules to get the Laplace transformation along with their properties, we will discuss in the next lecture. So meanwhile, until and unless we are coming with the next video, it is important to you keep trying to find out the different ROCs for the different respective channels. Hope so you will be able to understand this video. Meanwhile, you have a question, so please drop down your question here. Well, thank you very much. Let's see you again. Bye.